So in this section, we're going to focus on differentiability. And I'll admit there's not a ton of examples to go through with this. There are only a handful. And it's more of some concepts that flesh out what we talked about in the last section about how do we know if a function is differentiable or not differentiable. In other words, does the derivative or the slope of the function exist? So for a derivative to fail to exist, we have to remember that the definition of a derivative is a two-sided limit. So we're finding the slope between 2 points, and the limit moves them infinitely close together. Because it's a two-sided limit, it can fail for the same reasons any two-sided limit can fail. The most common reason being the left-hand derivative and the right-hand derivative aren't going to be the same. In other words, the slope from the right and the slope from the left aren't the same. And we actually saw that in the last section when we were playing around with some of the graphs. The other reason, which we haven't actually looked at yet, is when we calculate this limit, it could be infinite. So it could be approaching a positive or negative infinity. What that means is the function's going vertical. And that's rare because of the vertical line test with functions. But it is possible. And we'll look at kind of what does that look like. Now, rather than talking about where does a derivative exist, it's actually easier to talk about where does a derivative not exist. So a derivative does not exist at 4 places in a graph. One place is at a corner. So the absolute value of x is a great example of this. From the last section, we had linear piecewise functions that had corners on them. And we actually looked and saw the left-hand derivative and the right-hand derivative aren't the same where there's a corner. So wherever there's a corner in a graph, there is not going to be a derivative. The slope doesn't exist there. If we're asked for reasons, we do have to appeal to the fact that the left-hand derivative and the right-hand derivative are different. In this case, with the absolute value, my right-hand derivative has a value of -1. I'm sorry, +1, because over here the slope is 1. And the left-hand derivative has a value of -1, because over here the slope equals -1. Related to a corner is a cusp. Honestly, you can use the term corner and cusp interchangeably because with corners and cusps, a corner technically is made out of 2 linear pieces. If one of the pieces making the corner is not linear, we actually have what's called a cusp. When you were a little kid and you would draw pictures of scenery and you wanted to draw birds flying in the distance, you would draw them like this. You were actually drawing a cusp. But the idea of it is these are just corners that curve as we approach the point. So here I have x to the 2/3 power. It has a cusp at x equals 0. Well, where the cusp is, just like with the corner, the slopes aren't the same. I can see for the right-hand derivative that the slope is positive, whereas for the left-hand derivative, the slope is negative. And that's enough to tell me the left and right-hand derivatives aren't the same. So at 0, the derivative does not exist because the right-hand and left-hand derivatives are not the same. The third place that a derivative does not exist is a vertical tangent. Now, please note, this is a vertical tangent, not a vertical asymptote. Vertical asymptote is going to be coming up on the next slide here. A vertical tangent, my function is continuous. It just happens to be that at one specific point, when I draw the tangent line is a vertical line. So the function is continuous, it's the tangent that's vertical. And the issue there is because derivative is the slope, well, the slope of a vertical line doesn't exist because the slope's approaching an infinite value, and infinity is not a real number. So if I have a vertical tangent, the derivative does not exist because the slope is infinite. These are actually pretty rare. We don't come across these very often. Finally, the last place a derivative does not exist, and this is by far the most common, discontinuities. If we have any discontinuity at all, automatically derivative will not exist. And it depends on the discontinuity as far as why. The most common being right and left-hand derivatives aren't the same. So we see this with poles, with jumps, with oscillations, that the left and right-hand derivatives won't be the same. And I know that seems weird because if we look at the example I have graphed, the piecewise function where the function's -1 when x is less than 0, +1 when x is greater than or equal to 0, and make sure I include, there's a closed dot here and an open dot here. It looks like the slope on the right is 0 and the slope on the left is 0. So why aren't the derivatives the same? Well, it actually has to do with, remember, we're finding derivative by taking 2 points. So if I'm doing my right-hand derivative, I would be using my point of tangency, which is right here, because that's where the closed dot is, and then I would pick something a little bit to the right. Well, all of these slopes, so my right-hand derivative, is always going to be 0. But for my left-hand derivative, I'd be picking my point of tangency and a point a little bit to the left, which would be down here. And I can see from this that my left-hand derivative is not going to be 0. It's going to be some positive number. So my right-hand and left-hand derivatives aren't going to be the same. And this tends to be the issue pretty much with all of our discontinuities. One exception is some vertical asymptotes. You can get away with saying, well, my slopes are approaching infinity. Just because it's like a vertical tangent in that the closer you're getting, the more vertical your tangents are getting. But for the most part, with discontinuities, these are so common that pretty much if they ask you, well, how do you know your function is not differentiable? It's okay to just say, because there's a discontinuity. The other places it's not differentiable, we have to actually talk about, well, it's because left-hand and right-hand derivatives aren't the same, or because with a vertical tangent, the slope of the derivative is infinite. Or not the slope of the derivative, the slope of the function.